There is a wall in the history of the universe. Not a wall you can point to in space, not a wall that divides one region from another, but a wall in time, a moment before which our best instruments go completely silent and our best mathematics breaks down into nonsense. That moment is the Big Bang. Or more precisely, it is the moment approximately 10 to the power of negative 43 seconds after the Big Bang, the Planck time, the smallest interval of time that has meaning in current physics. Before that, the equations produce infinities. The density becomes infinite. The temperature becomes infinite. The curvature of spacetime becomes infinite. And in physics, when the equations produce infinities, it means one thing with remarkable consistency. Not that the universe actually contained an infinity, but that the theory being used to describe it has reached the edge of its own validity and is no longer telling you about reality. It is telling you about its own failure. The Big Bang singularity, the supposed point of absolute beginning, the moment from which all of space and all of time supposedly erupted, is not a description of what actually happened. It is a description of the moment when general relativity stops working, when the equations stop being a map of reality and start being a mirror of the theory's own limits. And what is on the other side of that wall, what was happening before or instead of the singularity, is one of the deepest and most consequential open questions in all of science. The Big Bang may not have been a beginning. It may have been a middle. Welcome to Dusk and Discovery. Tonight we go to the edge of what physics can currently describe and look at what the best theories say lies beyond it. If this is your first night here, this is the kind of thing we do. Lie back, get comfortable, subscribe if you want more nights like this. Now, let us go to the beginning, or the middle, depending on what the physics turns out to say. The standard story of the Big Bang is one of the most successful scientific narratives ever constructed. It begins approximately 13.8 billion years ago with the universe in an extraordinarily hot, dense, and uniform state. In the first fractions of a second, the fundamental forces are unified in a way we do not yet fully understand. In the first 10 microseconds, the quark-gluon plasma of the earliest moments cools enough for protons and neutrons to form. In the first 3 minutes, nuclear fusion produces the first atomic nuclei, hydrogen and helium and traces of lithium, in the specific ratios we observe today in the oldest stars and in the primordial gas clouds that have not been processed through stellar interiors. In the first 380,000 years, the universe cools enough for electrons to combine with nuclei into neutral atoms, making the universe transparent for the first time, and releasing the flood of photons we now detect as the cosmic microwave background. From there, over the following billions of years, gravity amplifies the tiny density fluctuations that were present at recombination into the galaxies and clusters and filaments of the cosmic web we observe today. This story is extraordinarily well confirmed. The predictions of Big Bang nucleosynthesis, the specific ratios of hydrogen to helium to deuterium to lithium produced in the first 3 minutes, match the observed abundances to high precision. The cosmic microwave background, detected in 1965, and mapped with increasing precision by the COBE and WMAP and Planck satellites, matches the predicted thermal spectrum and temperature fluctuation pattern, with a precision that ranks among the most accurate confirmations of any theory in science. The large-scale structure of the universe, the distribution of galaxies into the cosmic web, and the baryon acoustic oscillation scale, frozen into that distribution, matches the predictions of the standard cosmological model to within the measurement uncertainties. The success of the Big Bang model from the first 3 minutes onward is overwhelming and not seriously contested. But the success of the model from 3 minutes onward does not tell us what happened at time 0 or before. The equations of general relativity, extended backward in time from the well-confirmed later epochs, produce a singularity at time 0, a state of infinite density and infinite curvature from which the universe supposedly emerged. This singularity is not a prediction in the same sense that the helium abundance is a prediction. It is an extrapolation of the equations beyond the regime in which they are known to be valid. General relativity has been tested with extraordinary precision in regimes of moderate spacetime curvature, from the precession of Mercury's orbit to the bending of light around the Sun, to the gravitational waves from merging black holes. But at the densities and curvatures of the Big Bang singularity, the corrections from quantum mechanics, which general relativity ignores, are not small. They are enormous. They dominate. Applying general relativity to the Planck epoch is like applying Newtonian mechanics to describe electrons in atoms. You will get wrong answers, and the wrongness is systematic rather than incidental. The recognition that the Big Bang singularity is not physically real, but is instead a signal of the breakdown of general relativity at extreme conditions, is not a new or controversial idea. It is the mainstream view in theoretical physics. The singularity theorems proved by Penrose and Hawking in the 1960s and 1970s established that singularities are an inevitable consequence of classical general relativity under reasonable physical conditions. But these theorems assume the validity of classical general relativity, which is precisely what fails at the Planck scale. The general expectation, shared by essentially all physicists who work on quantum gravity, is that a correct theory of quantum gravity will resolve the Big Bang singularity, replacing it with a finite but extreme state that has a well-defined physical description. The question is what that description is, and whether it involves a prior state of the universe that preceded the Planck epoch. This is the question that has generated an extraordinary diversity of theoretical proposals over the past several decades, each one offering a different picture of what the Big Bang actually was and what, if anything, came before it. These proposals are not idle speculation. They are grounded in serious theoretical frameworks. They make specific predictions that can in some cases be compared to observations, and they differ from each other in ways that reflect genuine uncertainty about the correct theory of quantum gravity. The diversity of the proposals is not a sign of confusion, but of the frontier. Many ideas competing for theoretical traction, each one capturing some aspect of the problem while leaving others unresolved. The earliest and in some ways still the most complete of these proposals is the inflationary scenario, which was developed in the early 1980s primarily by Alan Guth, Andre Linde, Paul Steinhardt, and Andreas Albrecht. Inflation proposes that in the very early universe, a tiny fraction of a second after the Planck epoch, the universe underwent a period of exponential expansion driven by the potential energy of a scalar field called the inflaton. During inflation, the universe doubled in size every 10 to the negative 37 seconds or so, expanding by an enormous factor in an incredibly brief time. The total duration of inflation is uncertain, but is estimated to have lasted from roughly 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Planck epoch, an interval so brief that it is genuinely impossible to convey in everyday terms. In that interval, the volume of the universe expanded by a factor of at least 10 to the power of 78, and possibly by many more orders of magnitude. Inflation was proposed to solve three specific problems with the standard Big Bang model that were recognized in the late 1970s. The first is the horizon problem. The cosmic microwave background, the oldest light we can detect, is extraordinarily uniform in temperature across the entire sky, with variations of only 1 part in 100,000. But in the standard Big Bang without inflation, the regions of the early universe that produced the CMB light in different directions of the sky were never in causal contact with each other. They were so far apart that no light signal could have traveled from one to the other in the time available. How, then, did they come to be at the same temperature? Without inflation, this is a profound mystery. With inflation, it is solved. Before inflation began, the universe was small enough for all regions to be in causal contact, and to thermalize to a common temperature. Inflation then expanded these causally connected regions to the enormous scales we observe today, explaining why the CMB is so uniform. The second problem is the flatness problem. The geometry of the observable universe is extraordinarily close to flat, as established by measurements of the cosmic microwave background. In the standard Big Bang without inflation, maintaining this flatness requires the initial density of the universe to have been tuned to the critical density, with a precision of better than 1 part in 10 to the power of 60. Any deviation from this fine-tuning would have caused the universe to either collapse back into a big crunch or to expand so rapidly that no structure could form, in timescales far shorter than the current age of the universe. Inflation solves this problem by taking any initial geometry, however curved, and stretching it to such enormous scales that the observable portion is indistinguishable from flat, in the same way that the curved surface of the Earth appears flat on scales much smaller than the radius of curvature. The third problem is the monopole problem. Grand unified theories of particle physics predict that the high-energy conditions of the early universe should have produced magnetic monopoles, isolated north or south magnetic poles with no corresponding south or north pole, in enormous quantities. No magnetic monopole has ever been detected. Inflation solves this problem by diluting whatever monopoles were produced before or during inflation to such low density that the probability of finding one in the observable universe is negligible. Inflation solved all three problems with a single mechanism, which is a powerful argument for taking it seriously. But the most remarkable thing about inflation turned out to be something that was not fully appreciated at the time of its proposal. Inflation provides a natural mechanism for generating the tiny density fluctuation that seed all subsequent structure in the universe. During inflation, quantum fluctuations in the inflatoned field, the same kind of zero-point fluctuations that are present in all quantum fields, were stretched by the exponential expansion to macroscopic scales. These stretched quantum fluctuations produced tiny variations in the density of the universe after inflation ended, variations of 1 part in 100,000, which are exactly the fluctuations observed in the cosmic microwave background, and which grew under gravity to form the galaxies and clusters and cosmic web of the universe today. The specific statistical properties of the density fluctuations predicted by inflation, their near-Gaussian distribution, their near-scale invariant power spectrum with a slight tilt toward larger amplitudes at large scales, and the specific relationship between density fluctuations and gravitational wave fluctuations, are encoded in the pattern of temperature anisotropies in the CMB. The Planck satellite measured these properties with extraordinary precision and found them to be consistent with the predictions of simple inflationary models, with the spectral index of the scalar power spectrum, a parameter that characterizes the tilt of the spectrum, measured to be approximately 0.965, slightly less than the exactly scale-invariant value of 1 that the simplest inflationary models predict. This slight deviation from scale invariance is itself a prediction of inflation. The expansion was not exactly exponential, and the deviation from exact exponential expansion produces a slight tilt in the spectrum. The measured tilt is consistent with this prediction. Inflation also predicts a background of gravitational waves, tensor perturbations in the spacetime metric, produced by quantum fluctuations during the inflationary epoch. These gravitational waves would leave a specific imprint on the polarization of the CMB, a pattern called B-mode polarization, that is distinct from the polarization produced by density fluctuations. The detection of primordial B-mode polarization in the CMB would be direct evidence for inflation and would provide information about the energy scale at which inflation occurred. The search for primordial B-mode polarization is one of the most important objectives of current and future CMB experiments, including the BICEP and Keck array experiments in Antarctica and the proposed CMB-S4 experiment. The current measurements have established upper limits on the amplitude of the primordial gravitational wave background, but have not yet achieved a detection. Despite its many successes, inflation has a deep conceptual problem that is directly relevant to the question of whether the Big Bang was a beginning or a middle. The problem is called the measure problem or the eternal inflation problem, and it arises from the dynamics of the inflated field. In most models of inflation, the quantum fluctuations of the inflated field are large enough that, in some regions of space, the field rolls back up its potential rather than rolling down it, causing those regions to inflate faster and for longer than the surrounding regions. These faster inflating regions expand exponentially and produce more and more volume, generating an infinite sea of inflating space in which pocket universes like ours constantly nucleate. This process, called eternal inflation, has no end. Once inflation begins, it continues forever somewhere, even as it ends and gives way to hot Big Bang conditions in local pockets. Eternal inflation has two consequences that are important for tonight's question. The first is that it pushes the Big Bang from being the beginning of everything to being a local event in a much larger and much older process. In eternal inflation, our Big Bang was the moment when inflation ended in our particular pocket of the eternally inflating background, releasing the potential energy of the inflated field as a hot, dense plasma that then evolved through the standard Big Bang sequence. But this ending was preceded by an indefinitely long period of inflation in the background region, and that inflating background was itself produced by whatever initial conditions started the inflation. The Big Bang was not the beginning of the universe. It was the end of inflation in our local pocket, a transition from one phase of the universe's existence to another. The second consequence is that eternal inflation renders the predictions of inflation ambiguous in a disturbing way. If the inflating background produces infinitely many pocket universes, and if different pocket universes have different physical constants and different cosmological parameters, due to the different ways in which the inflated field can settle into different minima of the potential energy landscape, then predicting what observers in any given pocket universe will measure requires a way of comparing infinite numbers of observers in different pockets, which requires a measure. A way of assigning probabilities to different outcomes in an infinite ensemble. The measure problem is the problem of defining such a measure, and it has not been solved. Without a solution to the measure problem, the predictions of eternal inflation are ambiguous, and the framework loses much of its predictive power. The measure problem is not just a technical difficulty. It reflects a deeper issue about the nature of the inflationary multiverse and the status of physical predictions in a universe that is infinite in the relevant sense. If the multiverse produces every possible outcome infinitely many times, then the concept of probability, which requires a way of comparing relative frequencies, becomes ill-defined in a fundamental way. The measure problem is a manifestation of the tension between the predictive ambition of science and the infinite complexity of the multiverse that eternal inflation implies. Setting aside the measure problem for the moment, the most important question for tonight's narrative is whether eternal inflation extends infinitely into the past, whether the inflating background itself had a beginning or has existed forever. The theorem proved by Board, Guth, and Vilenkin in 2003 provides a partial answer. The BGV theorem states that any spacetime that has been, on average, expanding throughout its history must have an incomplete geodesic, a path through spacetime that cannot be extended infinitely far into the past, which implies that the spacetime has a past boundary, a beginning. The theorem applies to the eternally inflating background of inflationary cosmology, where the average expansion rate is positive. This means that eternal inflation, despite its name, cannot be past eternal. It must have had a beginning. The BGV theorem is a purely classical result, applying to classical spacetimes described by general relativity. It does not tell us what happened at the past boundary, whether the boundary is a genuine singularity or a smooth quantum gravitational state or a transition from a different phase of the universe. It establishes only that the inflating background cannot have been expanding forever, that there must have been a beginning of some kind. What kind of beginning is precisely the question that quantum gravity must answer, and it is the question around which the most interesting theoretical proposals of the past few decades have been organized. One class of proposals takes the BGV theorem at face value and posits a genuine beginning, a moment before which there was no time and no space, from which the universe emerged in a specific quantum gravitational state. The proposal of this kind that has received the most attention and generated the most discussion is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in 1983. The no-boundary proposal is formulated in the language of Euclidean quantum gravity, a technique in which the time coordinate is replaced by an imaginary time coordinate, producing a spacetime with 4 spatial dimensions rather than 3 spatial dimensions and 1 temporal dimension. In this Euclidean formulation, the universe is described by a smooth, closed 4-dimensional space with no boundary, no edge, no beginning, and no end. The proposal says that the quantum state of the universe is given by a path integral over all compact Euclidean 4 geometries that match the given boundary conditions on a 3-dimensional spatial surface, and that this sum, called the no-boundary wave function, gives the amplitude for the universe to be in any given state. The no-boundary proposal has a specific and beautiful implication for the question of what came before the Big Bang. Nothing. Not nothing in the sense of empty space, which is itself a physical state with quantum fields and vacuum energy. Nothing in the sense of no time, no space, no prior state. The no-boundary proposal says that the universe simply is, described by the no-boundary wave function, and that asking what happened before the Big Bang is like asking what is north of the North Pole. The question sounds meaningful but has no answer, not because our knowledge is limited, but because the concept of before does not apply. Time is a dimension of the universe, not a container in which the universe exists, and the no-boundary proposal says that time had its beginning at the beginning of the universe, in the same way that the spatial dimensions had their boundaries at the spatial boundary of the universe. The no-boundary proposal is mathematically elegant and conceptually clear, but it has faced significant theoretical challenges in recent years. Calculations by Feldbrugge, Leiners, and Turok, published in 2017 and 2018, suggested that the no-boundary wave function, when computed using the correct semi-classical approximation methods, predicts a universe that is highly irregular rather than smooth, with large fluctuations rather than the small fluctuations observed in the CMB. This would seem to contradict the observed flatness and uniformity of the universe, and would undermine one of the central motivations for the no-boundary proposal. The debate about whether these calculations are correct and what they imply for the no-boundary proposal is ongoing, with Hartle, Hawking, and Hertog disputing the interpretation and arguing that the no-boundary proposal remains viable when correctly formulated. The controversy illustrates the difficulty of calculating in quantum gravity and the sensitivity of the results to the specific mathematical choices made in the calculation. A different class of proposals does not posit a genuine beginning, but instead proposes that the Big Bang was a transition from a prior phase of the universe, a bounce, or a tunneling event, or a phase transition from which the current expanding phase emerged. These proposals make the Big Bang a middle rather than a beginning in the most direct sense. There was something before, something that preceded the hot, dense plasma of the standard Big Bang, and the transition between that something and the expanding universe we inhabit is what we call the Big Bang. The simplest and most physically motivated of the bounce proposals is loop quantum cosmology, an application of loop quantum gravity to the homogeneous, isotropic universe described by the Friedmann equation. Loop quantum gravity, as we mentioned in the black hole video, is a theory of quantum gravity in which spacetime is not continuous but discrete at the Planck scale, with the geometry of space being represented by a network of discrete quantum states called spin networks. In loop quantum cosmology, the application of this discrete quantum geometry to the cosmological setting produces a correction to the Friedmann equation that becomes significant at densities approaching the Planck density, roughly 10 to the power of 96 kilograms per cubic meter. At these extreme densities, the quantum geometry effects provide a repulsive pressure that counteracts the gravitational attraction and prevents the collapse to a singularity. Instead of reaching infinite density, the collapsing universe reaches a maximum density of the Planck density and then bounces, the contraction reveering into an expansion. The Big Bang singularity is replaced by a quantum bounce, a moment of minimum volume and maximum density from which the universe re-expands. In the loop quantum cosmology picture, the universe before the Big Bang was a contracting universe, a universe that had been expanding in its prior phase, reached a maximum size, turned around, and contracted through the big bounce into the expanding phase we now inhabit. The prior contracting universe is not a separate universe created by different initial conditions, but the same physical universe, described by the same physical laws, going through a different phase of its evolution. The Big Bang is not a beginning. It is a transition, a moment of maximum compression from which the universe re-expands in the phase we call the Big Bang and the subsequent cosmic history. Loop quantum cosmology makes specific predictions about the state of the universe emerging from the Big Bounce, predictions that differ from the predictions of standard inflation, and that prediction is specific, and the search for its signature is an active area of research. The loop quantum cosmology bounce scenario raises an immediate and fascinating question. What was the prior contracting universe like? If the universe before the Big Bang was contracting, what was it contracting from? Was there a maximum size it reached before beginning to contract? And if so, what determined that maximum size, and was there a universe before that maximum, expanding toward it? The picture suggests an oscillating universe, bouncing repeatedly between maximum and minimum sizes, with each bounce producing a new expanding phase and each expansion eventually reveering into a new contraction. But the details of what happens to the structure and the thermodynamics of the universe across multiple bounces are not fully worked out, and whether the bounce scenario can be extended to a truly eternal cycling, or whether the BGV-like arguments apply to the contracting phase and require a beginning there, as well, is an active area of investigation. There is a related but distinct set of proposals, inspired by string theory rather than loop quantum gravity, that also propose a pre-Big Bang contracting phase. The ekpyrotic scenario, proposed by Paul Steinhardt, Neil Tirach, and their collaborators in 2001, is motivated by the structure of extra dimensions in string theory, and proposes that the Big Bang was a collision between two three-dimensional branes, higher dimensional membrane-like objects that are fundamental entities in string theory, moving through a higher dimensional space. In the ekpyrotic scenario, the universe we inhabit is a three-dimensional brane, and the Big Bang was the result of this brane colliding with another brane, with the kinetic energy of the collision being converted to the hot, dense plasma of the early universe. The ekpyrotic scenario makes specific predictions for the density fluctuations in the CMB that differ from the predictions of inflation in a specific way. Inflation predicts a nearly scale-invariant spectrum of both scalar and tensor perturbations, while ekpyrosis predicts a nearly scale-invariant scalar spectrum, but essentially no tensor perturbations. The detection or non-detection of primordial gravitational waves in the CMB polarization is therefore a potential discriminant between inflation and ekpyrosis. The current upper limits on the tensor-to-scalar ratio from CMB observations are constraining, but have not yet been sensitive enough to conclusively rule out either scenario. The next generation of CMB polarization experiments, currently under development, will push these limits significantly and may provide the decisive test. The cyclic extension of the ekpyrotic scenario, called the cyclic model, proposes that the brain collision has occurred repeatedly throughout an infinite past, with each collision producing a new Big Bang and a new expanding phase that eventually reaches maximum size. The brains pull together again, and the cycle repeats. In the cyclic model, the universe has no beginning. The Big Bangs are transitions between cycles, not absolute origins. The entropy produced in each cycle dilutes over the subsequent expansion, so that the next cycle begins in a low entropy state suitable for structure formation, addressing the thermodynamic question of how the ordered low entropy conditions of the Big Bang can be maintained across multiple cycles. Roger Penrose's conformal cyclic cosmology, which we discussed in the vacuum episode, and which appears repeatedly across these nights because it intersects so many of the deep questions we have been exploring, offers yet another picture of the Big Bang as a middle. In CCC, the universe cycles through eons, with the heat death of each eon serving as the Big Bang of the next through a conformal rescaling of the metric. The Big Bang of our universe is the conformally transformed heat death of the previous eon, and our heat death will be the Big Bang of the next. The Big Bang is not a beginning. It is a transition between eons, a mathematical boundary surface in the conformal geometry of the universe that connects the featureless maximum entropy end state of one eon to the hot, dense initial state of the next. What all of these proposals share: inflation and eternal inflation, and the no-boundary proposal and loop quantum cosmology, and the ekpyrotic and cyclic models and Penrose's CCC, is a recognition that the Big Bang singularity of classical general relativity is not the true beginning of the universe, but the edge of the domain of validity of the theory. Beyond that edge, something happens that general relativity cannot describe, and the different proposals are different guesses about what that something is. They are distinguished from each other by the specific quantum gravitational framework they employ, by the specific pre-Big Bang state they propose, and by the specific predictions they make for observables like the CMB power spectrum and the primordial gravitational wave background. The question of which proposal is correct is not currently answerable from available observations. The observational constraints on the pre-Big Bang epoch are extremely limited, precisely because the hot, dense plasma of the early universe acted as a screen, erasing most of the information about what preceded it. The quantum fluctuations imprinted on the CMB come from the inflationary epoch, not from before inflation, and the CMB itself comes from the surface of last scattering, not from the Planck epoch. The window into the pre-Big Bang epoch, if there was one, is narrow and may remain permanently narrow. Gravitational waves from the inflationary epoch, if detected in the CMB polarization, would confirm that inflation occurred and constrain its energy scale, but would not directly probe what came before inflation. A detection of the pre-inflationary features predicted by loop quantum cosmology or the ekpyrotic scenario would provide more direct evidence for a specific pre-Big Bang scenario, but detecting such features requires measurements at scales at or beyond the edge of the observable universe, which may be permanently inaccessible. Despite this observational limitation, the theoretical investigation of pre-Big Bang cosmology is not merely speculative. It is constrained by the requirement that the pre-Big Bang state, whatever it was, must produce the specific initial conditions of the post-Big Bang universe that we observe. The universe emerging from the Big Bang was extraordinarily smooth and low entropy, with density fluctuations of 1 part in 100,000 and a geometry indistinguishable from flat. Any pre-Big Bang scenario must be capable of producing these conditions, either by deriving them from the pre-Big Bang dynamics or by showing that they are generic outcomes of the transition from the pre-Big Bang phase to the post-Big Bang phase. This is a non-trivial constraint that eliminates many possible pre-Big Bang scenarios and provides guidance for those that remain viable. The smoothness and low entropy of the Big Bang initial conditions is itself one of the deepest puzzles of cosmology, as we discussed in the expiration date video. Roger Penrose has argued that the initial conditions of the Big Bang were extraordinarily improbable, with an entropy so low that the probability of selecting them at random from all possible initial conditions is 1 in 10 to the power of 10 to the power of 123. In Penrose's view, this improbability is not explained by inflation, because the inflationary models themselves require specific low-entropy initial conditions to get started, merely pushing the fine-tuning problem back one step. Penrose argues that the low entropy of the Big Bang is the most important unsolved problem in cosmology, and that its solution requires either a specific theory of initial conditions, such as the no-boundary proposal or CCC, or a fundamentally different understanding of the arrow of time and the second law of thermodynamics. The low entropy of the Big Bang is connected to the arrow of time in a way that is worth making explicit. The second law of thermodynamics says that entropy increases over time, that the future is always higher entropy than the past. But this statement is asymmetric in a way that the microscopic laws of physics are not. The microscopic laws of physics, as far as we know, are time-symmetric. They work the same way forward and backward in time. The asymmetry of the second law is therefore not built into the microscopic laws, but arises from the specific boundary conditions of the universe. The reason entropy increases toward the future rather than the past is that the past has lower entropy than the present, which in turn is because the Big Bang was a low entropy state. The arrow of time points away from the Big Bang because the Big Bang was extraordinarily ordered, and everything since has been the universe exploring the vastly larger space of higher entropy configurations. If the Big Bang was a middle rather than a beginning, if there was a prior phase of the universe, then the question of where the low entropy of the Big Bang came from becomes even more pressing. The low entropy cannot simply have been present in the prior phase, because the second law requires entropy to increase, and a prior phase that had lower entropy than the Big Bang would itself require explanation, pushing the problem back indefinitely. The pre-Big Bang scenario must either explain how low entropy conditions are naturally produced at the bounce or transition point, or must propose a different relationship between the pre-Big Bang and post-Big Bang phases, in which entropy is reset rather than accumulated. Loop quantum cosmology addresses this through the specific dynamics of the bounce, arguing that the quantum corrections to the Friedmann equation that prevent the singularity also naturally produce low-entropy initial conditions on the other side of the bounce. The ekperiodic cyclic model addresses it through the dilution of entropy over the long expansion phase between bounces, arguing that by the time the branes approach each other again, the entropy density is low enough that the next cycle begins in a state of manageable entropy. Penrose's CCC addresses it by arguing that the low entropy of the Big Bang is a consequence of the conformal geometry of the transition between eons, in which the massive particle content that would carry entropy is absent at the conformal boundary. Each proposal offers a different mechanism for the entropy reset, and evaluating these mechanisms requires a more complete understanding of the quantum gravitational dynamics at the bounce or transition point than we currently possess. What ties all of these threads together, and what makes the question of whether the Big Bang was a beginning or a middle so consequential, is that the answer determines the context in which the universe exists. If the Big Bang was an absolute beginning, then the universe came into existence from literally nothing, and the laws of physics and the initial conditions that have governed everything since are facts about the universe that have no further explanation within physics. They are brute facts, the boundary conditions of existence. If the Big Bang was a middle, if there was a prior phase that produced the conditions of the Big Bang, then the laws and initial conditions of our universe are not brute facts but consequences, derivable in principle from the dynamics of the prior phase and the transition between phases. The universe is older than we thought, and its apparent initial conditions are actually derived conditions, the output of a process that preceded what we call the beginning. This is not a minor distinction. It changes the entire framing of the deepest cosmological questions. The question of why the universe exists, which is unanswerable if the Big Bang was an absolute beginning, becomes the question of why the prior phase that produced our Big Bang existed, which may be answerable within a larger theoretical framework. The question of why the physical constants have the values they have, which requires the anthropic multiverse or a theory of initial conditions if the Big Bang was a beginning, may have a more direct answer if the constants are determined by the dynamics of a pre-Big Bang phase. The question of why entropy was so low at the Big Bang, which is mysterious and essentially unexplained if the Big Bang was a beginning, becomes the question of why entropy resets at the transition between phases, which is at least a question that the specific dynamics of the transition can potentially answer. The Big Bang may have been a middle. The evidence for this is indirect and the specific scenario is unknown, but the theoretical arguments are compelling, and the observational programs currently underway are asking exactly the right questions to constrain the possibilities. The wall in the history of the universe, the moment beyond which our current theories go silent, is not necessarily a wall at the edge of existence. It may be a wall at the edge of our current knowledge, and what is on the other side of it may be not nothing but something older and stranger and more continuous than the standard picture of cosmic origins has allowed us to imagine. The wall at the edge of our knowledge is not silent because nothing is behind it. It is silent because the instruments we built to listen were designed for a universe that began, not for one that continued. The cosmic microwave background, which is the oldest electromagnetic signal we can detect, was released 380,000 years after the Big Bang, when the plasma of the early universe thinned enough for photons to travel freely for the first time. Everything before that is electromagnetically dark, not because nothing was happening, but because the universe was opaque. The standard Big Bang story, remarkable and precise as it is, begins at 380,000 years and speaks with diminishing confidence as we push it backward in time toward the Planck epoch. What we are trying to do when we ask whether the Big Bang was a beginning or a middle is to push through the opacity, through the silence, and find out what the universe was doing before it let us look. The tools for this are not telescopes. They are theoretical. A telescope cannot see before the surface of last scattering, but a theoretical framework that correctly describes the physics of the transition from a pre-Big Bang phase to a post-Big Bang phase would leave specific imprints on the CMB and on the large-scale structure that we can measure. The pre-Big Bang phase would not be directly visible, but its fingerprints would be written into the initial conditions of the post-Big Bang phase, and those initial conditions would be encoded in the oldest observable signals. This is why the theoretical proposals we surveyed in Part 1 are not purely philosophical. They are scientific in the sense that they make specific predictions for things we can observe, even if what they are describing happened before we can observe. To understand what kind of fingerprints a pre-Big Bang phase might leave, it helps to think carefully about what information can survive a transition between phases. If the transition involves a bounce, a moment of maximum compression after which expansion begins, then the question is what physical quantities are preserved across the bounce and what are reset. If the transition involves a tunneling event, a quantum mechanical transition from one vacuum state to another, then the question is what properties of the prior vacuum are inherited by the tunneling state. If the transition involves a conformal rescaling, as in Penrose's CCC, then the question is what geometrical and thermodynamic information survives the conformal transformation. In each case, the answer is different, and the specific imprints on the post-Big Bang universe are correspondingly different. In loop quantum cosmology, the bounce preserves certain correlations between modes of the quantum fields that were present in the pre-bounce contracting phase. These correlations manifest in the post-bounce expanding phase as modifications to the primordial power spectrum at very large scales. Specifically, the loop quantum cosmology bounce predicts a suppression of the amplitude of density fluctuations at scales comparable to or larger than the current Hubble radius, because the quantum corrections to the Friedmann equation that prevent the singularity also affect the evolution of the longest wavelength modes of the quantum fields. This suppression would appear in the CMB temperature power spectrum as a deficit of power at the lowest multipoles, the largest angular scales on the sky. Intriguingly, there is a known anomaly in the CMB temperature power spectrum at exactly these scales. The observed power at the lowest multipoles, particularly the quadrupole and octopole, is lower than the prediction of the standard inflationary model with no pre-Big Bang phase. This anomaly has been known since the WMAP observations and has been confirmed by Planck. The statistical significance of the anomaly is moderate, roughly 2 to 3 sigma depending on the method of assessment, and there is debate about whether it represents a genuine deviation from the predictions of standard inflation or a statistical fluctuation in a universe where the lowest multipoles are inherently poorly sampled by a single sky. But the anomaly exists, and loop quantum cosmology predicts it qualitatively, which has led some researchers to take seriously the possibility that the suppression at low multipoles is a signature of the pre-Big Bang bounce. The challenge is specificity. A suppression of power at large scales is predicted by many different modifications of the standard inflationary scenario, not just loop quantum cosmology, and the current measurements are not precise enough to distinguish between the different models. What would be needed to confirm the loop quantum cosmology interpretation is a more detailed characterization of the shape of the suppression, the specific way in which the power falls off at different scales, and a comparison with the specific predictions of loop quantum cosmology models with different choices of the pre-bounce initial conditions. This is a calculation that has been done for some models but not in full generality, and the comparison with data is ongoing. Beyond the power spectrum, loop quantum cosmology predicts specific non-Gaussian features in the CMB, deviations from the Gaussian statistics of the standard inflationary model that arise from the quantum gravitational corrections at the bounce. Non-Gaussianity is a sensitive probe of the physics of the early universe because it encodes higher-order correlations between the density fluctuations that are not captured by the power spectrum alone. The standard inflationary model predicts small non-Gaussianity of a specific form, characterized by a parameter called FNL that is small and of a specific sign and shape. Different models of inflation and pre-inflationary physics predict different values and shapes of FNL. The Planck satellite has measured FNL with sufficient precision to constrain many models, and the measurement is consistent with the standard single-field slow-roll inflation prediction of small Gaussianity. But the uncertainties are still large enough to allow the non-Gaussianity signatures of loop quantum cosmology bounce models. Future CMB experiments, including the Simons Observatory, CMB S4, and the proposed space missions LightBird and PICO, will measure the CMB temperature and polarization anisotropies with significantly better sensitivity and angular resolution than Planck. They will improve the constraints on non-Gaussianity and on the large-scale power spectrum, potentially providing the discrimination between standard inflation and pre-inflationary scenarios that current data cannot achieve. They will also improve the sensitivity to the B-mode polarization, that is the signature of primordial gravitational waves, which is one of the most important discriminants between inflation and the alternatives. The primordial gravitational wave background deserves special attention as a probe of pre-Big Bang physics, because Different scenarios make dramatically different predictions for its amplitude and spectrum. Standard single-field slow-roll inflation predicts a gravitational wave background, whose amplitude is related to the energy scale of inflation, with the ratio of tensor to scalar perturbations, called R, ranging from near zero for low-energy inflation to approximately 0.1 for high-energy inflation near the gut scale. The measurement of R therefore constrains the energy scale of inflation directly. The ekpyrotic and cyclic scenarios predict a gravitational wave background with an amplitude that is negligibly small for all practical purposes, because the collision of branes in the ekpyrotic scenario does not produce significant tensor perturbations. A detection of primordial gravitational waves at any amplitude detectable by current or planned experiments would essentially rule out the ekpyrotic scenario as the explanation for the density fluctuations. Conversely, a confirmed non-detection of primordial gravitational waves down to very low values of R would provide evidence against high-energy inflation and would be consistent with either low-energy inflation or the ekpyrotic scenario. Loop quantum cosmology predicts a gravitational wave background that is also suppressed relative to the standard inflationary prediction, because the bounce dynamics modify the evolution of tensor modes in the same way that they modify the scalar modes. The specific amplitude depends on the details of the pre-bounce state and the dynamics of the bounce, and a range of predictions is possible within the loop quantum cosmology framework. Some models predict a tensor-to-scalar ratio that is significantly smaller than the standard inflationary prediction at the same energy scale, which would appear as a deficit in the B-mode polarization signal. Penrose's conformal cyclic cosmology makes yet another distinct prediction. The signals that CCC predicts in the CMB are not in the power spectrum or the non-Gaussianity, but in specific localized features called Hawking points, which are the imprints of the final evaporation events of supermassive black holes in the previous eon. As we discussed in the vacuum episode, Penrose and his colleagues have claimed to have found rings of anomalously low temperature variance in the CMB that they interpret as the Hawking radiation from black holes in the previous eon. The claim is contested, with multiple groups finding no statistically significant signal above what is expected from standard inflationary fluctuations. The debate is ongoing and illustrates the difficulty of distinguishing genuine signatures of pre-Big Bang physics from statistical fluctuations in a noisy signal. The gravitational wave background is also accessible through means other than the CMB. The direct detection of a primordial gravitational wave background, as distinct from the stochastic background from astrophysical sources like binary mergers that we discussed in the vacuum episode, is one of the most ambitious goals of next-generation gravitational wave observatories. The pulsar timing arrays have recently detected a gravitational wave background at nanohertz frequencies that is consistent with, but not yet confirmed to be, a contribution from the inflationary era or from cosmic strings or other early universe sources. The LISA space-based detector, planned for launch in the 2030s, will be sensitive to millihertz frequency gravitational waves that could include contributions from phase transitions in the early universe at energies much higher than accessible to current detectors. And the proposed Einstein telescope and Cosmic Explorer ground-based detectors will extend gravitational wave detection to higher frequencies and greater sensitivity, potentially revealing the gravitational wave background from the earliest moments of the expanding phase. Each of these observational windows is probing a different epoch of the early universe and a different aspect of the physics of the transition from the pre-Big Bang phase to the post-Big Bang phase. Together, they are constructing a picture of the universe's earliest moments that will become progressively more constraining over the next decade and beyond. The question of whether the Big Bang was a beginning or a middle may not be answerable from a single observation, but it may become increasingly constrained as multiple observational programs provide consistent or inconsistent evidence for specific scenarios. The theoretical landscape of pre-Big Bang cosmology is not just a collection of isolated proposals. It is organized around a set of deep conceptual questions that any viable proposal must address, and understanding these questions is essential for evaluating the proposals. The deepest of these questions, deeper even than the specific dynamics of the bounce or the tunneling or the conformal transition, is the question of time itself. What does it mean for time to have a beginning? Is time a fundamental feature of reality or an emergent property of a deeper timeless framework? And if there was a phase before the Big Bang, was time the same in that phase as it is in ours? The nature of time in quantum gravity is one of the most contested and most profound questions in theoretical physics. In classical general relativity, time is one of the four dimensions of spacetime, and it is distinguished from the spatial dimensions by the signature of the metric, the specific way in which time contributes to the spacetime interval. Time flows, in the sense that events have a temporal order and physical processes have a direction, from past to future, that is correlated with the increase of entropy. But in quantum mechanics, time has a different and more ambiguous status. In the Schrödinger equation, time is an external parameter, a background against which the quantum state evolves, not itself a quantum observable subject to the uncertainty principle and superposition. This asymmetry between the treatment of time in general relativity and in quantum mechanics is one of the deepest tensions between the two theories and is one of the central challenges for any theory of quantum gravity. In the Wheeler-DeWitt equation, the quantum cosmological analog of the Schrödinger equation derived from canonical quantum gravity, time does not appear. The Wheeler-DeWitt equation is an equation for the wave function of the universe that has no explicit time dependence. This is the problem of time in quantum gravity. The fundamental equation that is supposed to describe the quantum evolution of the universe does not contain time. The interpretation of this result is highly contested. Some physicists take it at face value as evidence that time is not fundamental at the deepest level, that it is an emergent quantity that appears when you consider certain limits or certain decompositions of the full quantum gravitational system into a background and perturbations. In this view, the universe does not evolve in time. It simply is, described by a timeless wave function, and the appearance of time is an emergent property of the specific quantum state the universe happens to be in. Julian Barbour, the British physicist who has written extensively on the nature of time, has argued for the most radical version of this position, that time is entirely illusory, that the universe is a static collection of configurations called nows, and that what we experience as the flow of time is the correlation between the records of the past encoded in the current state and the relative probabilities of different configurations. In Barbour's Platonia, as he calls the timeless space of all possible configurations, there is no time, no flow, no duration. There are only configurations, some more probable than others, and the appearance of time arises from the structure of the correlations between the information encoded in each configuration. Barbour's view is philosophically provocative, but faces the challenge of explaining why the specific configurations we observe are ordered in such a way that the correlations we call memories point toward a consistent past, why the physical records of the past, the geological layers, the fossil record, the cosmic microwave background, all point toward a coherent history rather than a randomly selected collection of configurations. Barbour argues that this is a consequence of the specific structure of the quantum mechanical probability distribution over configurations, which strongly favors configurations that contain the kind of complexity and structure we observe. Whether this argument can be made rigorous and quantitative is a matter of ongoing debate. A different approach to the problem of time in quantum gravity is provided by the relational view of time, developed by Carlo Rovelli and others in the context of loop quantum gravity. In the relational view, Time is not an external parameter or a fundamental dimension of spacetime, but a relational quantity, defined by the correlations between physical degrees of freedom. There is no absolute time that flows independently of matter. There is only the relative change of one physical system with respect to another, and what we call time is the specific correlation between physical clocks and other physical processes. In this view, the Big Bang is not a beginning of time in an absolute sense, but a boundary of the domain in which the relational time defined by the physical clocks of the post-Big Bang universe is well defined. Before the bounce, a different relational time, defined by the degrees of freedom of the pre-bounce contracting universe, may have been well defined, and the transition between the two relational times at the bounce is what we call the Big Bang. The question of whether time is fundamental or emergent is not just a philosophical curiosity. It has direct implications for the question of what it means for the Big Bang to be a beginning or a middle. If time is fundamental and is a dimension of spacetime, then asking what came before the Big Bang is a question about a time before which there was no time, which may be as meaningless as asking what is north of the North Pole. If time is emergent, defined by the correlations between physical degrees of freedom, then there may be a well-defined sense in which the universe had a prior phase, even if the specific time coordinate of the post-Big Bang universe was not well defined in that prior phase. The bounce in loop quantum cosmology, for example, is a transition between two phases of a universe that is described by the same Wheeler-DeWitt timeless quantum state, with the relational time defined differently in the contracting and expanding phases. The relationship between time and the second law of thermodynamics is also relevant here. The arrow of time, the direction from past to future that the second law defines, is connected to the low entropy of the Big Bang. If the Big Bang was a middle, if there was a prior phase, then the question of the entropy in that prior phase becomes pressing. The second law requires that entropy increases toward the future. If we run time backward from the Big Bang, entropy should increase in the backward direction as well. This means that the era before the Big Bang, going backward in time from the Big Bang, should have had higher entropy than the Big Bang. But higher entropy before the Big Bang, in the contracting phase, raises the question of why the contraction occurred from a higher entropy state, and how a contracting high-entropy universe could produce the low-entropy conditions of the Big Bang at the bounce. This thermodynamic argument is one of the most serious objections to the bounce scenarios, and different proposals address it differently. In loop quantum cosmology, the bounce dynamics are argued to naturally reset the entropy, with the quantum corrections to the Friedmann equation producing a moment of minimum entropy at the bounce from which the entropy increases in both temporal directions. The arrow of time in both the pre-bounce and post-bounce phases points away from the bounce, with entropy increasing in both directions from the moment of minimum size and minimum entropy. This is a symmetric picture of time, in which the universe before the Big Bang had a time arrow pointing backward from the bounce, opposite to our own time arrow, and the two eras are thermodynamically symmetric about the bounce. The symmetric picture of time across the bounce is philosophically interesting, but observationally challenging. If the universe before the bounce had its arrow of time pointing in the opposite direction, then observers in the pre-bounce universe, if any existed, would have experienced their future as what we would call the deeper past, moving away from the bounce in the direction of increasing entropy in their time direction. They would not have been able to observe the bounce as an event in their future, because the bounce was in the direction of their past, the direction of decreasing entropy. And we cannot observe the pre-bounce universe directly, because the information about it that survives the bounce is limited to what is encoded in the specific quantum state of the universe at the bounce point. The idea that the universe before the Big Bang had an opposite arrow of time is reminiscent of the two-sided cosmology proposed by Sean Carroll and Jennifer Chen, in which the universe started from a low-entropy patch that spontaneously fluctuated from equilibrium, and then evolved in two temporal directions simultaneously, with each direction having its own arrow of time pointing away from the initial low-entropy patch. In Carroll and Chen's picture, the Big Bang is not the beginning of time, but the thermodynamic center of a universe that extends in both temporal directions, with our universe being one of the two branches. The universe before the Big Bang in this picture is thermodynamically symmetric to our universe, with the same kinds of structures and the same kinds of observers, experiencing their time as running in the direction opposite to ours. The Carroll-Chen proposal addresses the fine-tuning of the Big Bang initial conditions in a specific way. The low entropy of the Big Bang is not a mystery, because the Big Bang is not the absolute beginning, but a point in the interior of a much larger eternal spacetime. The spacetime as a whole has high entropy, because it extends indefinitely in both temporal directions from the initial low-entropy patch. The low entropy at the Big Bang is explained by the specific quantum state of the initial patch from which the universe grew, and the existence of observers in our branch is explained by the anthropic selection of a branch with low enough entropy to permit structure formation. Each of these theoretical frameworks, loop quantum cosmology, the ekpyrotic and cyclic models, Penrose's CCC, the Carroll-Chen two-sided cosmology, the Hartle-Hawking no-boundary proposal, addresses a different aspect of the question of what the Big Bang was and what came before it. None of them is established. None of them has clear and unambiguous observational support. Each of them has theoretical virtues and faces theoretical challenges. Together, they represent the state of the field, a collection of serious, mathematically developed proposals for the pre-Big Bang universe, organized around a set of deep conceptual questions about the nature of time and entropy and quantum gravity, waiting for the observational data that will eventually constrain or eliminate some of them and provide support for others. What this landscape of proposals reveals about the current state of physics is something important and worth dwelling on. The question of whether the Big Bang was a beginning or a middle is not a settled question. It is not a question that the standard model of cosmology answers, because the standard model is explicitly agnostic about what happened before the Planck epoch. The standard model describes the universe from the first fraction of a second onward with extraordinary precision, but it does not and cannot say what happened at time zero or before. The proposals we have been discussing are attempts to extend the description beyond the range of the standard model into the regime where a theory of quantum gravity is required, and none of them has yet achieved the status of an established part of the standard picture. This is the frontier. This is where the knowledge ends and the speculation, informed and constrained but genuine speculation, begins. It is a frontier that is being actively explored by some of the most capable physicists alive, using the most sophisticated theoretical and mathematical tools available, and it is a frontier that the next generation of observational experiments will push further. The question of what came before the Big Bang is not unanswerable in principle. It is unanswered in practice, waiting for the combination of better theory and better data that will eventually resolve it. The resolution, when it comes, will almost certainly require a complete theory of quantum gravity. Because the physics of the Big Bang singularity and its replacement is quantum gravitational physics by definition. The three leading candidates for quantum gravity, string theory, loop quantum gravity, and causal set theory, each offer different pictures of the Planck epoch and different mechanisms for resolving the singularity. String theory resolves the singularity by replacing the point-like structure of general relativity with extended strings whose minimum length provides a natural ultraviolet cutoff, preventing the infinite compression of the singularity. Loop quantum gravity resolves it through the discrete quantum geometry of space, which provides a minimum volume below which further compression is prevented by quantum effects. Causal set theory resolves it through the fundamental discreteness of spacetime at the Planck scale, which prevents the continuous metric of general relativity from developing the infinite curvature of the singularity. Each of these approaches has been applied to the cosmological setting, and each produces a different picture of the pre-Big Bang phase. String theory's approach to pre-Big Bang cosmology includes the pre-Big Bang scenario of Gasparini and Veneziano, the ekpyrotic and cyclic scenarios of Steinhardt and Tirach, and the landscape of eternal inflation motivated by the string theory potential energy landscape. Loop quantum gravity's approach includes the loop quantum cosmology bounce scenario and the spin foam models of quantum cosmology. Causal set theory's approach to cosmology is less developed, but points toward a fundamentally discrete and stochastic cosmogenesis in which the universe grows by the addition of discrete spacetime events according to a probabilistic rule. The diversity of approaches reflects the genuine uncertainty about the correct theory of quantum gravity, which is itself one of the most important unsolved problems in physics. Progress on the pre-Big Bang cosmology question and progress on the quantum gravity question are therefore tightly coupled. Advances in understanding the quantum gravity theory will constrain the pre-Big Bang cosmology proposals, and conversely, the specific requirements of a cosmological scenario that successfully explains the observed properties of the universe may constrain the quantum gravity theory. The interplay between theory and observation, between quantum gravity and cosmological observation, is what will eventually lead to progress on both questions simultaneously. The observational programs that are most relevant to this interplay are the ones focused on the earliest observable signals from the universe. The CMB is the primary source of information about the early universe accessible with current technology, and the next generation of CMB experiments will push the precision of CMB measurements significantly beyond what Planck achieved. They will search for the B-mode polarization signature of primordial gravitational waves, which constrains the energy scale of inflation and potentially the specific model of inflation. They will measure the non-Gaussianity of the CMB with greater precision, constraining the specific dynamics of the inflationary or pre-inflationary phase. And they will look for specific features in the large-scale power spectrum, including the suppression at low multipoles predicted by loop quantum cosmology and the specific patterns predicted by CCC. Beyond the CMB, the 21-centimeter line of neutral hydrogen offers a potential window into the universe at earlier times than the CMB can probe. The 21-centimeter line is produced by the spin-flip transition in atomic hydrogen, and it can be used to map the distribution of neutral hydrogen in the universe before and during the epoch of reionization, when the first stars and galaxies ionized the neutral hydrogen gas that had filled the universe since recombination. The hydrogen epoch of reionization array, the low-frequency array in Europe, and the planned square-kilometer array are developing the capability to map the 21-centimeter signal across large volumes of the universe at redshifts of 6 to 30, corresponding to epochs between 200 million and 500 million years after the Big Bang. At even higher redshifts, corresponding to earlier epochs, the 21-centimeter signal could in principle probe the distribution of matter as early as a few million years after the Big Bang, providing information about the primordial density fluctuations at scales and epochs that the CMB cannot access. The 21-centimeter signal at high redshifts is particularly interesting because it is sensitive to the global history of reionization and to the properties of the first stars, which in turn depend on the initial conditions left by inflation or the pre-inflationary phase. Specific features in the 21-centimeter global signal, such as the depth and shape of the absorption trough that is expected when the first stars began producing Lyman alpha photons, encode information about the timing and nature of the first stars. The EDGES experiment, which detected a signal at the predicted redshift in 2018, found a trough that was significantly deeper than standard models predicted, suggesting either a colder than expected intergalactic medium or a warmer than expected radio background at that epoch. The interpretation of the EDGES result is debated and has not been confirmed by subsequent experiments, but it illustrates the potential of 21-centimeter cosmology to reveal unexpected features of the early universe. The earliest structures that formed in the universe, the first stars and the first galaxies, are being observed with the James Webb Space Telescope at redshifts of 10 to 15, corresponding to epochs between 200 and 500 million years after the Big Bang. The properties of these first structures, their masses, their star formation rates, their chemical compositions, encode information about the initial conditions from which they formed and the specific dynamics of the early universe. As we noted in the universe distance video, some of the early James Webb results suggest that the first galaxies may be more massive and more evolved than standard models predict, which could be a sign of modifications to the initial conditions or to the dynamics of early structure formation that are not captured by the standard inflationary model. The possibility that the James Webb observations at high redshift reveal something unexpected about the early universe is significant not just for galaxy formation models, but for the question of the Big Bang itself. If the initial conditions of the post-Big Bang universe are not precisely what standard inflation predicts, if there are systematic deviations at specific scales or epochs, then those deviations may be signatures of the pre-Big Bang phase. The challenge is disentangling the effects of the pre-Big Bang physics from the effects of the astrophysical processes that govern the formation and evolution of the first galaxies, which are themselves complex and not perfectly understood. But the combination of CMB measurements and high redshift galaxy observations and 21-centimeter cosmology, constrained by a consistent theoretical framework, offers the possibility of a multi-probe determination of the initial conditions that could reveal the fingerprints of whatever came before the Big Bang. The theoretical developments that are most likely to provide decisive guidance in this landscape are those that succeed in making the quantum gravity resolution of the Big Bang singularity explicit and calculable. The current proposals, loop quantum cosmology and the ekpyrotic model and Penrose's CCC and the others, are either approximate or rely on specific assumptions about the quantum gravitational dynamics that have not been fully derived from a fundamental theory. A more complete and more fundamental calculation, one that starts from the full quantum gravity theory and derives the specific quantum state of the universe at the bounce or transition point without approximation, would provide predictions that are both more reliable and more specific than the current proposals. This is the goal toward which the quantum gravity community is working, and progress is being made. In loop quantum gravity, the spin foam models of quantum cosmology are being developed to provide a fully covariant description of the quantum bounce, without relying on the homogeneous, isotropic approximation of loop quantum cosmology. In string theory, the computation of the string theory landscape and the specific transition rates between different vacuum states is being refined, providing a more detailed picture of how the inflationary multiverse selects the specific vacuum we inhabit. In holographic approaches inspired by the AD-SCFT correspondence, the quantum description of cosmological spacetimes is being constructed using the dual boundary field theory, which may eventually provide a complete and consistent description of the Big Bang transition, without relying on the semi-classical approximations that produce the singularity. Each of these theoretical programs is long-term and involves formidable technical challenges, but the direction is clear and the motivation is strong. The question of what the Big Bang was is too fundamental and too consequential to leave unanswered if the tools to answer it can be developed. The universe is telling us, through the specific pattern of temperature fluctuations in the CMB, and the specific distribution of galaxies and the specific values of the cosmological parameters, what the initial conditions were. What it is not yet telling us is where those initial conditions came from, whether they were the output of a prior phase or the input to an absolute beginning. That is the question that the combination of better theory and better observation is working toward, and the answer will be one of the most significant discoveries in the history of science. What we can say now, with the theory and the observations we currently have, is this: the Big Bang singularity of classical general relativity is not a reliable description of what happened at time zero. It is a mathematical artifact of the theory reaching the edge of its validity. Beyond that edge, something happened. The most developed and most physically motivated proposals for what that something was all involve a prior phase of the universe, whether a bouncing contraction, a colliding brain, a conformal transformation from a previous eon, or a nucleation from a timeless quantum state. None of these proposals has been confirmed. None of them should be taken as established. But collectively, they represent the consensus view of the theoretical community about the direction in which the answer is most likely to lie. Not in an absolute beginning from nothing, but in a transition from something that preceded what we call the beginning. The Big Bang may have been a middle. The weight of theoretical argument, if not yet of observational evidence, tilts in that direction. And what that means for our understanding of the universe, for the question of what the universe is and how long it has existed, and what it was before it became what it is now, is the question we have been circling all night, and will spend the remainder of tonight approaching from the remaining angles that have not yet been explored. The remaining angles are not small ones. They are the questions that the history of science almost never asks directly because they sound too large, too philosophical, too close to the territory that religion and metaphysics have traditionally claimed as their own. But they are scientific questions in the sense that matters. They are questions whose answers have observational consequences, questions that specific theoretical frameworks address in specific and testable ways, questions that the physics cannot avoid if it takes seriously the proposal that the Big Bang was a middle. The questions are these: what was actually happening in the Planck epoch, the moment of maximum compression, when the physics we know becomes unreliable? What does the wave function of the universe look like in the quantum gravitational description? And what does it mean for a universe to be described by a wave function? And what are the implications for the concept of a beginning if the correct picture turns out to be one in which the universe had no beginning at all? Start with the Planck epoch, because it is the physical reality that all the theoretical frameworks are trying to describe, and its specific character determines what any pre-Big Bang scenario must accommodate. The Planck epoch is the interval from time 0 to approximately 10 to the negative 43 seconds after the Big Bang. The Planck time is the time it takes light to cross the Planck length, which is approximately 1.6 times 10 to the negative 35 meters, the shortest length that has physical meaning in current theory. At earlier times, the density of the universe was above the Planck density, approximately 5 times 10 to the 96 kilograms per cubic meter, and the curvature of spacetime was above the Planck curvature, approximately 10 to the 66 per square meter. At these densities and curvatures, the quantum uncertainty in the spacetime metric is comparable to the metric itself, meaning that the very geometry of spacetime is fluctuating wildly, rather than being a smooth background on which quantum fields propagate. The phrase wildly fluctuating geometry of spacetime is one that sounds dramatic, but is difficult to make precise without a specific theory of quantum gravity. What it means, qualitatively, is that in the Planck epoch the concept of a smooth, well-defined spacetime geometry breaks down. Spacetime at the Planck scale is not a smooth four-dimensional manifold with a well-defined metric. It is something more like a quantum superposition of many different geometries, each with different topologies and different curvatures, all existing simultaneously in a quantum mechanical sense, and only settling into a definite classical geometry when the density drops below the Planck density, and the quantum gravitational fluctuations become small relative to the background metric. John Wheeler, one of the physicists who pioneered the study of quantum gravity in the 1950s and 1960s, called this state of the Planck epoch spacetime foam. The image is of a spacetime whose geometry at the Planck scale is as turbulent and as topologically complex as sea foam, with microscopic wormholes and handles and other topological features constantly forming and dissolving on timescales of the Planck time. Wheeler's spacetime foam is a qualitative description rather than a precise calculation, and different approaches to quantum gravity give different specific pictures of what the Planck epoch looks like. But the underlying idea that the smooth spacetime of general relativity is replaced by something fundamentally quantum and geometrically complex at the Planck scale is widely accepted. In loop quantum gravity, the Planck epoch is described by the dynamics of spin networks, the quantum states of spatial geometry in which space itself has a discrete granular structure at the Planck scale. The smooth, three-dimensional space of everyday experience and of general relativity is, in loop quantum gravity, an approximation to a fundamentally discrete network of quantum geometric degrees of freedom, in the same way that the smooth continuum of a material like glass is an approximation to the discrete atomic structure that underlies it. At the scales of everyday experience, the discreteness is irrelevant because the individual quantum geometric units are far too small to be detected. At the Planck scale, the discreteness is everything, determining the dynamics in ways that are qualitatively different from the smooth, general relativistic dynamics. The specific dynamics of spin networks in the Planck epoch are described by spin foam models, the four-dimensional extension of spin networks that describes the evolution of the quantum geometry through time. A spin foam is a quantum superposition of different histories of the spin network, each history corresponding to a different way in which the quantum geometry could evolve. The amplitude for a given spin foam history is calculated from the specific transition amplitudes between different spin network states, which are determined by the loop quantum gravity action. The full quantum gravity path integral, summing over all possible spin foam histories, gives the transition amplitude between any two quantum gravitational states, and this amplitude determines the probability of observing any given classical spacetime geometry as the low-energy limit of the full quantum calculation. In the cosmological context, the spin foam calculation of the transition through the Planck epoch gives the specific quantum state of the universe emerging from the bounce. This quantum state encodes the probabilities for different classical spacetimes to emerge from the bounce, including the probability for the specific classical spacetime we observe, with its specific value of the Hubble parameter, its specific density fluctuation amplitude, its specific geometry and topology. The calculation is technically demanding and has been carried out only approximately, using simplifications of the full spin foam model. But the direction is clear. The classical spacetime of the post-Planck universe is a specific coarse-grained description of the quantum gravitational state that emerged from the bounce, and the specific classical properties we observe, including the flatness and the specific amplitude of the density fluctuations, are encoded in the probabilities determined by the spin foam calculation. In string theory, the Planck epoch is described differently, through the dynamics of strings rather than the discrete geometry of loop quantum gravity. In string theory, the fundamental constituents of the universe are not point particles but one-dimensional objects, strings, whose minimum length is the string length, which is related to the Planck length by the string coupling constant. At energy densities comparable to the string scale, the usual picture of a smooth spacetime background on which strings propagate breaks down, and the string dynamics become dominant. The specific behavior of strings at high densities, including the phenomenon of T-duality, in which the physics at very small length scales is equivalent to the physics at very large length scales, suggests that the Big Bang singularity is avoided in a specific way in string theory. The contraction of the universe towards small sizes does not produce an infinite density singularity, but instead undergoes a T-duality transformation that maps the collapsing small-scale physics to an expanding large-scale physics. This T-duality-inspired picture of the Big Bang in string theory is the foundation of the pre-Big Bang scenario of Gasparini and Veneziano, which proposes that the universe before the Big Bang was in a dilaton-dominated phase, a phase in which the scalar field called the dilaton, which controls the strength of the string coupling, was evolving in a specific way that produced an accelerating collapse rather than a simple matter-dominated collapse. The T-duality transformation at the moment of maximum compression then maps this collapsing phase to the expanding phase of the post-Big Bang universe, making the Big Bang a T-duality bounce rather than a classical singularity. The pre-Big Bang phase in this scenario was characterized by very weak string coupling, very large distances, and very low curvature, the opposite of the post-Big Bang phase, with the T-duality transformation connecting the two. The pre-Big Bang scenario makes specific predictions for the spectrum of gravitational waves produced during the pre-Big Bang phase, which is different from the prediction of standard inflation, because the dynamics of the dilaton field during the pre-Big Bang phase produce tensor perturbations with a blue spectrum, increasing power at small scales, rather than the nearly scale-invariant or slightly red spectrum of inflation. This prediction of a blue gravitational wave spectrum is potentially detectable by space-based gravitational wave observatories at millihertz frequencies, where the LISA detector will have its peak sensitivity. The detection of a stochastic gravitational wave background with a blue spectrum would be evidence for the pre-Big Bang scenario, or for other early universe models that produce a blue spectrum, distinguishing them from standard inflation. The question of what the universe actually looked like in the Planck epoch, in the physical sense of what a hypothetical observer in that epoch would have experienced, is one that the different theories approach differently, and that has no definitive answer in any of them. In loop quantum cosmology, the Planck epoch involves a moment of maximum compression in which the physical distances between all points in space are at their minimum values, of the order of the Planck length, and the energy density of matter and radiation is at its maximum, of the order of the Planck density. The quantum geometry is in its most compressed state, with the discrete spin network structure of space at its finest resolution. The bounce dynamics produce a period of extremely rapid change in which the contraction reverses into an expansion in a Planck time, after which the expansion continues, and the universe evolves through the standard Big Bang sequence. The experience of this epoch, if experience is the right word for what happens in a regime where the concept of individual observers is itself questionable, would be unlike anything in the post-Big Bang universe. The energy density is so extreme that all known particles are in thermal equilibrium with each other, and with the gravitational field, with temperatures of the order of the Planck temperature, approximately 1.4 times 10 to the 32 degrees Kelvin. The concept of distinct particles, of electrons and quarks and photons and gravitons as separate entities, breaks down in this regime because the energy scale is above any known mass threshold, and the quantum gravitational corrections to particle interactions are of order 1, comparable to the leading order interaction amplitudes. The physics of the Planck epoch is the physics of a unified quantum gravitational system, in which the usual distinctions between different types of matter and different forces have dissolved into a single structure, whose correct description requires the full theory of quantum gravity. This dissolution of the familiar distinctions is what makes the Planck epoch both so interesting and so inaccessible. It is interesting because it is the regime where all the forces and all the matter and all the geometry of the universe are at their most unified, where the structure that gave rise to everything we observe was at its most compressed and most symmetric. It is inaccessible because the unified structure at the Planck scale is precisely the thing that our current theories cannot describe. General relativity and the standard model of particle physics, both extraordinarily accurate in their respective regimes, both break down at the Planck scale in ways that are individually understood but collectively unresolved. The resolution of the tension between them, which is the content of the as yet undiscovered theory of quantum gravity, is precisely what determines what the Planck epoch was like, and how the transition from the pre-Big Bang phase to the post-Big Bang phase occurred. The wave function of the universe is the object in quantum cosmology that is supposed to describe the state of the entire universe, including the spacetime geometry and the matter fields, in the quantum gravitational regime. The concept of a wave function for the universe was proposed by de Wit in 1967 and developed by Hartle and Hawking into the no-boundary proposal, and it represents the most ambitious application of quantum mechanics to the largest possible system, the universe as a whole. In ordinary quantum mechanics, the wave function of a system encodes the probability amplitudes for different possible states of the system, and measurement collapses the wave function to a specific state. The wave function of the universe cannot be collapsed by external measurement because there is no external observer. The universe is everything, and any measurement is an event inside the universe, not outside it. This raises the question of how the predictions of the wave function of the universe are to be interpreted. If there is no external observer to collapse the wave function, in what sense does the universe have a definite state? The two main interpretations of quantum mechanics offer different answers. In the Copenhagen interpretation, which posits that the wave function collapses upon measurement by an observer, the wave function of the universe is problematic because there is no external observer to perform the measurement. The Copenhagen interpretation, which works well for ordinary quantum systems observed by external observers, seems ill-suited for the quantum description of the entire universe. The many-worlds interpretation, developed by Hugh Everett in 1957, offers a different picture that is more natural for quantum cosmology. In the many-worlds interpretation, the wave function never collapses. Instead, when a quantum system interacts with a measuring apparatus, the wave function of the combined system evolves into a superposition of all possible outcomes, each outcome existing in a different branch of the wave function. The observer in each branch experiences the specific outcome in that branch, and the different branches are mutually decoherent, meaning that they do not interfere with each other on any practically accessible timescale. The many-worlds interpretation is a unitary description of quantum mechanics in which the wave function always evolves deterministically according to the Schrödinger equation, and the apparent randomness of quantum measurement is a consequence of the observer's ignorance of which branch they are in. Applied to the wave function of the universe, the many-worlds interpretation says that the universe is described by a single universal wave function that encompasses all possible classical histories simultaneously. Different branches of the wave function correspond to different classical universes, different configurations of spacetime and matter that are all simultaneously present in the wave function, but mutually decoherent. Our classical universe, the specific spacetime we observe with its specific cosmological history and its specific physical laws and constants, is one branch of the universal wave function. Other branches contain other classical universes, potentially with different physical histories and different configurations of matter, all existing simultaneously in the sense that they are all present in the wave function. This many-worlds interpretation of the wave function of the universe is the natural quantum mechanical description of eternal inflation, in which different pocket universes correspond to different branches of the wave function of the eternally inflating background. It is also the natural description of the no-boundary proposal, in which the no-boundary wave function assigns amplitudes to different classical spacetimes, and the classical spacetimes that are predicted with high amplitude by the no-boundary wave function are the ones that are most likely to be observed. The many-worlds interpretation removes the problem of the external observer in quantum cosmology. The different branches of the universal wave function are self-contained, each one containing its own observers who experience their specific branch as the definite classical universe. The many worlds interpretation applied to quantum cosmology has specific implications for the question of whether the Big Bang was a beginning or a middle. If the universe is described by a universal wave function, then the question of what came before the Big Bang is a question about the structure of the wave function in the quantum gravitational regime near the Planck epoch. In the no-boundary proposal, the wave function is defined on compact Euclidean geometries with no boundary, and the question of what came before is answered by saying that the concept of before does not apply. The wave function assigns amplitudes to different classical histories, and each classical history has a specific beginning at the Big Bang, but the wave function itself is timeless, defined on all possible geometries simultaneously without reference to any particular time direction. In the many worlds interpretation of loop quantum cosmology, the wave function of the universe encompasses both the pre-bounce contracting phase and the post-bounce expanding phase simultaneously, with the bounce being a region of the wave function where the quantum gravitational effects are maximal and the classical description breaks down. The pre-bounce and post-bounce phases are both branches of the same wave function, connected by the quantum gravitational dynamics of the bounce. In this picture, there is a sense in which the universe before and after the Big Bang are the same universe, described by the same wave function, going through different phases. The Big Bang is a transition in the wave function, not a beginning of the wave function. The decoherence of the different branches of the wave function of the universe is what produces the appearance of a classical spacetime from the quantum gravitational description. Decoherence is the process by which quantum superpositions become effectively classical through their interaction with an environment, with the different branches of the superposition becoming entangled with different states of the environment, and thereby losing their ability to interfere with each other. In the case of the wave function of the universe, the decoherence of the large-scale geometry of spacetime from the microscopic quantum gravitational degrees of freedom produces the classical geometry of the post-Planck universe, with the quantum gravitational fluctuations of the Planck epoch becoming the classical density fluctuations that seed structure formation. The specific way in which quantum gravitational fluctuations in the Planck epoch decohere into classical density fluctuations in the post-Planck universe is a key calculation in quantum cosmology, and it has been carried out in different ways in different theoretical frameworks. In inflation, the decoherence of the quantum fluctuations of the inflatoned field is what produces the classical density fluctuations that appear as temperature anisotropies in the CMB. The squeezing of the quantum state during inflation, the specific way in which the quantum fluctuations are amplified by the exponential expansion and become classical, is well understood in the semi-classical approximation and is the mechanism by which quantum mechanics generates the seeds of all cosmic structure. In loop quantum cosmology, the analogous decoherence of the quantum bounce fluctuations into classical density fluctuations is less well understood, but is the subject of active calculation. The transition from a quantum to a classical description is not just a technical issue, but a conceptual one that goes to the heart of what the Big Bang was. If the Planck epoch was a genuinely quantum gravitational regime, with no well-defined classical geometry, then the Big Bang, the moment of transition from the quantum regime to the classical expanding universe, is better understood as a decoherence event than as a singularity. The universe did not begin at the Big Bang in the sense of coming into existence from nothing. Instead, the quantum gravitational state of the Planck epoch decohered, producing a specific classical spacetime geometry with a specific set of initial conditions, and the subsequent evolution of this classical geometry is what we call the history of the universe from the Big Bang onward. The Big Bang is the moment of classicalization, not the moment of creation. This picture of the Big Bang as a decoherence event rather than a creation event has profound implications for the question of what came before. If the Big Bang is a decoherence event, then before the Big Bang was not nothing but the quantum gravitational state that decohered. That state had a specific structure, encoded in the wave function of the universe, and the specific classical spacetime that emerged from the decoherence was determined by that structure. The question of what came before the Big Bang is therefore the question of what the wave function of the universe was in the Planck epoch, which is the central question of quantum cosmology. The no-boundary proposal gives one answer. The wave function was defined by the sum over compact Euclidean geometries, and the specific classical spacetime that emerged was the one with the highest amplitude in the no-boundary wave function. The loop quantum cosmology bounce gives another answer. The wave function in the Planck epoch was the quantum state of the collapsing pre-bounce universe, and the specific classical spacetime that emerged was determined by the quantum dynamics of the bounce. The ekpyrotic scenario gives a third answer. The wave function in the Planck epoch was the quantum state of the two colliding branes, and the specific classical spacetime that emerged was determined by the details of the brane collision. Each answer is a different picture of the quantum state in the Planck epoch, and a different mechanism for the classicalization that produced the post-Big Bang universe. The philosophical implications of a universe without a beginning are worth exploring carefully, because they touch on questions that have been central to human thought about existence and time for millennia. The idea that the universe had a beginning, that there was a first moment from which everything else followed, is deeply embedded in many philosophical and religious traditions. The Christian concept of creation ex nihilo, creation from nothing, posits a God who creates the universe from absolute non-existence, with the Big Bang being the scientific analog of the moment of creation. The appeal of this picture is not just religious. It also resolves the question of why the universe exists at all, by positing a creator who brought it into existence. If the universe had no beginning, if it has existed eternally or in some cyclic or quantum gravitational sense that transcends the concept of a beginning, then the question of why it exists does not have the simple answer of a creator who made it. Leibniz asked, "Why is there something rather than nothing?" And the question has haunted philosophy ever since. If the Big Bang was an absolute beginning, then the something of our universe came from nothing, and the question of why it came into existence rather than remaining nothing is unanswerable within physics. Physics describes the evolution of the universe from given initial conditions, but cannot answer why there are any initial conditions at all, why there is something that has initial conditions rather than no thing at all. This is the deepest version of the fine-tuning problem, not just why the physical constants have the values they have, but why there is anything physical at all. If the Big Bang was a middle, however, then the question shifts. The universe did not come from nothing. It came from something, a prior state, whether a bouncing contraction or a colliding brane or a previous eon or a timeless quantum gravitational state. And the question of why there is something rather than nothing becomes the question of why that prior state existed, which in turn may lead to a prior state, in an infinite regress that never actually reaches nothing. If the correct picture is one in which the universe has no beginning, in which there is always something and there was never nothing, then the question of why there is something rather than nothing may be replaced by the question of why there is this specific something rather than some other something, which is a question that physics might eventually answer through the specific dynamics of the quantum gravitational state. The physicist and philosopher Derek Parfit argued that the question why is there something rather than nothing may have the simplest possible answer, because nothing is the least likely option. In a quantum mechanical universe, there are many more ways to have something than to have nothing, because nothing requires that all quantum fields be in a specific state of absolute zero energy, while something requires only that some fields are in some state. The probability of having something, given the quantum mechanical rules, is overwhelmingly larger than the probability of having nothing. This argument, if correct, would dissolve the question of why there is something rather than nothing without invoking any specific initial conditions or any creator. Something is simply overwhelmingly more probable than nothing in any quantum mechanical framework. The argument has philosophical critics who question whether the concept of probability applies to the question of whether something exists at all, which is prior to any context in which probabilities can be defined. But it illustrates the direction in which physics is moving when it takes seriously the quantum mechanical description of the universe from its earliest moments. The question of why there is something rather than nothing is being transformed from a metaphysical question, with no scientific answer, into a question about quantum gravitational initial conditions that may eventually be addressable within the framework of physics. The specific implications of a universe without a beginning for the concept of time are also worth exploring. If the universe has always existed, if there was no first moment, then time itself has no beginning in the physical sense. Time is a property of the universe, a dimension of the spacetime that constitutes the universe. And if the universe is eternal, then time is eternal. But eternal time raises its own puzzles. If time is infinite in both directions, into the past and into the future, then the probability of being at any specific moment in the infinite past is zero. And the question of why we are in this specific era rather than any other has no statistical answer. The Boltzmann brain problem, which we discussed in the expiration date video in the context of the infinite future, also applies to the infinite past. In an infinite past, the probability of the universe spontaneously fluctuating into the specific low-entropy state of the Big Bang is non-zero, and given infinite time it would have happened infinitely many times. The specific Big Bang that produced our universe would then be just one of infinitely many such fluctuations, selected by the anthropic condition that observers can only exist in universes with sufficiently low entropy after the Big Bang. This is the Boltzmann cosmology, the proposal that the universe as we observe it is a statistical fluctuation from a prior state of maximum entropy, and it was taken seriously in the late 19th and early 20th centuries before the discovery of the expanding universe. The discovery that the universe is expanding, and that the expansion has been going on for a finite time, ruled out the Boltzmann cosmology in its original form. Because a universe that has been expanding for 13.8 billion years is not in thermal equilibrium and cannot be the result of a fluctuation from maximum entropy on any timescale consistent with the observed age. But the Boltzmann cosmology lurks as a possibility in any eternal universe scenario, and the challenge for any pre-Big Bang proposal is to explain why the Big Bang was a specific physical transition rather than a random statistical fluctuation. The loop quantum cosmology bounce scenario addresses this by proposing a specific physical mechanism, the quantum gravitational bounce, that naturally produces a low-entropy expanding phase from a contracting phase. The bounce is not a random fluctuation, but a deterministic consequence of the quantum gravitational dynamics. The ekpyrotic scenario addresses it by proposing a specific brane collision that naturally produces low-entropy initial conditions. Penrose's CCC addresses it by proposing a conformal rescaling that maps the high-entropy end of one eon to the low-entropy beginning of the next through a geometrical transformation rather than a statistical fluctuation. Each proposal provides a physical mechanism that avoids the statistical challenge of the Boltzmann cosmology. The question of what the universe was like in the Planck epoch and what came before also has implications for the question of whether the physical laws themselves had a beginning or have always been the same. If the Big Bang was an absolute beginning, then the physical laws came into existence with the universe, or they were present in the quantum gravitational state that gave rise to the universe, as external constraints on what could happen at the Big Bang. If the Big Bang was a middle, then the physical laws were present in the prior phase as well, governing the dynamics of the pre-Big Bang universe, and the question of where the laws came from is pushed back to an earlier time or to the quantum gravitational state that preceded the observable universe. There is a provocative possibility, explored by Lee Smolin in his cosmological natural selection proposal, that the physical constants themselves have evolved over cosmic time through a process analogous to biological natural selection. Smolin proposes that black holes give birth to new universes through a quantum gravitational process at the singularity inside the black hole, with the new universe inheriting the physical constants of the parent universe, but with small random variations. Universes with physical constants that produce many black holes are more reproductively successful and produce more offspring universes, leading over cosmic time to a selection for physical constants that maximize black hole production. The physical constants of our universe, including the values of the fundamental masses and coupling constants, would then be the result of this cosmological natural selection, optimized for black hole production by the selection process. Smolin's proposal is speculative and faces significant theoretical challenges, including the absence of a well-defined mechanism for the inheritance of physical constants across the black hole singularity, and the question of whether the selection pressure for black hole production actually favors the specific constants of our universe. But the underlying idea that the physical constants might have a dynamical history that extends beyond our observable universe, and that might have evolved through some selection process, is a natural extension of the pre-Big Bang cosmology framework and illustrates the kind of questions that become available when the Big Bang is understood as a middle rather than a beginning. The deep connection between the question of what came before the Big Bang and the question of why the physical constants have the values they have is one of the most important threads in contemporary theoretical physics. Both questions are fundamentally about the initial conditions of the observable universe, about why the universe we inhabit has the specific properties it has rather than different ones. If the Big Bang was an absolute beginning, then the initial conditions are brute facts, the boundary conditions of existence, and the best available explanation for their specific values is the anthropic selection from a multiverse of different initial conditions. If the Big Bang was a middle, then the initial conditions are derived from the dynamics of the prior phase, and the explanation for their specific values is in principle calculable from the theory of the prior phase. This distinction between brute facts and derived facts is philosophically significant. Science has a long history of transforming apparent brute facts into derived consequences of deeper theories. The apparent brute fact that the Earth is approximately 93 million miles from the Sun was transformed into a derived consequence of the initial conditions of the solar system and the dynamics of gravitational orbit formation. The apparent brute fact that atoms are the fundamental constituents of matter was transformed into a derived consequence of the quantum mechanics of electrons and nuclei. The apparent brute fact that the physical constants of the Standard Model have specific values is the current frontier of this process of transformation, and the proposal that the Big Bang was a middle is one of the most direct approaches to this transformation. If the constants are derived from the pre-Big Bang dynamics, then they are not brute facts, but consequences, and the question of why they have their specific values has a scientific answer. The night, the quiet, the specific hours when the question of what came before the beginning becomes possible to sit with rather than dismiss, is the right context for this kind of thinking. The universe is old enough, and the physics is developed enough, that the question is no longer purely metaphysical. It has specific content, specific theoretical frameworks that address it, specific observational programs that constrain it. The wall at the beginning of time is real in the sense that our current theories cannot penetrate it, but it is not necessarily permanent. The theory of quantum gravity, when it is developed to the point of making specific and testable predictions about the Planck epoch and what preceded it, will either confirm that the Big Bang was an absolute beginning or reveal that it was a middle, a transition from a prior phase that has specific physical content and specific observable consequences. The universe may be telling us already, in the pattern of temperature anomalies at large scales in the CMB, and in the properties of the first galaxies detected by the James Webb Space Telescope, and in the gravitational wave background detected by the pulsar timing arrays, that something unusual happened at or before the earliest observable epoch. The signals are subtle, their interpretation is contested, and the connection to specific pre-Big Bang scenario is not yet established. But they are the kinds of signals that a pre-Big Bang scenario would produce, the kinds of fingerprints that a prior phase would leave in the initial conditions of the post-Big Bang universe. And the fact that they are present at all is a reason to take seriously the possibility that the Big Bang was a middle. The silence before the Big Bang, the opacity of the early universe to electromagnetic observation, the breakdown of classical general relativity at the Planck epoch, are not proofs that there was nothing before. They are limits of our current observational and theoretical capabilities. The universe before the Big Bang, if it existed, was not required to announce itself in ways that our current instruments are designed to detect. It was required only to leave the right initial conditions for the universe after the Big Bang, and those initial conditions are what we observe in the CMB and in the large-scale structure, and in the properties of the first galaxies. Reading those initial conditions back to their source, tracing them through the Planck epoch to whatever preceded it, is the ultimate goal of quantum cosmology, and the progress that has been made toward that goal over the past 50 years, from the formulation of the Wheeler-DeWitt equation, to the no-boundary proposal, to the loop quantum cosmology, bounce to the detection of the gravitational wave background by pulsar timing arrays, represents genuine progress toward an answer to the oldest and deepest question that physics can ask. Genuine progress. That phrase deserves to be examined before we move past it, because the history of cosmology is littered with proposals that looked like progress and turned out to be wrong, and distinguishing genuine progress from sophisticated speculation is one of the most important and most difficult tasks in science at its frontier. The proposals we have been exploring, the loop quantum cosmology bounce, the ekpyrotic scenario, the no-boundary wave function, Penrose's conformal cyclic cosmology, are all serious theoretical frameworks developed by serious physicists using the best available mathematical tools. But they are also all unconfirmed, none of them supported by decisive observational evidence, all of them in competition with each other, and with the standard picture of inflation followed by a simple hot Big Bang. In what sense, then, is there genuine progress? The progress is real, but it is progress of a specific kind. It is progress in understanding what the question actually is, in sharpening the formulation of the problem to the point where specific theoretical answers can be attempted, and specific observational tests can be proposed. 50 years ago, the question of what happened before the Big Bang was not a scientific question in any meaningful sense. It was a philosophical or theological question, outside the reach of any theoretical framework and any observational program. Today it is a scientific question with multiple competing theoretical answers, each of which makes specific predictions for the CMB and the gravitational wave background and the properties of the first galaxies. The question has been scientified, brought within the reach of the scientific method, and the specific observational tests that will constrain the answers are within the reach of instruments that either exist or will exist within the next decade. That is genuine progress, even if the final answer is not yet in. The most complete current picture of the Big Bang as a middle, assembled from the theoretical threads we have been following across all four parts of tonight's exploration, looks something like this. The universe we observe emerged approximately 13.8 billion years ago from a state of extreme density and temperature in the Planck epoch, which was characterized by quantum gravitational dynamics that cannot be described by classical general relativity. The specific quantum gravitational state of the Planck epoch was determined by whatever preceded it, and that preceding state was itself physical, not nothing. The transition from the preceding state to the post-Planck expanding universe was a physical process, governed by the dynamics of quantum gravity, and the specific outcome of that process, the specific initial conditions of the post-Planck universe, was determined by the dynamics rather than being an arbitrary brute fact. In the loop quantum cosmology picture, the most developed and most physically explicit of the bounce scenarios, the picture is as follows. The universe before the Big Bang was a contracting universe, evolving according to the same quantum gravitational laws that govern the current expanding universe. As the contracting universe reached the Planck density, the quantum corrections to the Friedmann equation became significant and eventually dominant, producing a repulsive quantum gravitational pressure that reversed the contraction. The moment of minimum volume, maximum density, and maximum quantum gravitational correction is what we call the Big Bang. After the bounce, the universe expanded, cooling rapidly, and within the first fraction of a second, the density had dropped below the Planck density, and the quantum gravitational corrections had become negligible. The subsequent evolution, from the Planck epoch to the present, is accurately described by the standard Big Bang model, with inflation providing the mechanism for generating the density fluctuations. In this picture, the inflation that followed the bounce is not in conflict with the bounce. It is a consequence of it. The specific quantum state of the universe at the bounce naturally produces the conditions required for inflation to begin. A universe with a specific energy density dominated by the potential energy of a scalar field, which then drives the exponential expansion of the inflationary phase. The bounce provides the initial conditions for inflation, and inflation provides the mechanism for generating the density fluctuations. The two are sequential phases of a single continuous process that began in the contracting pre-bounce universe, passed through the quantum gravitational bounce, and emerged into the expanding universe we observe today. This combination of bounce and inflation is sometimes called the LQC inflation scenario, and it is the most developed version of the loop quantum cosmology framework for cosmology. It inherits the observational successes of inflation, including the flat geometry, the near-scale invariant power spectrum, and the specific temperature anisotropies of the CMB. It adds to these the specific imprint of the bounce at large scales, the suppression of power at the lowest multipoles, which is a distinctive prediction that goes beyond standard inflation, and that can in principle be confirmed or refuted by measurements of the large-scale CMB power spectrum. The Penrose CCC picture, the most aesthetically complete of the cyclic proposals, gives a different but equally specific picture. The universe before the Big Bang was a previous eon, a universe that began in its own Big Bang, expanded through its own stelliferous era, and reached its own heat death as the last black holes evaporated. In the heat death state, the universe was filled with a uniform bath of massless radiation, with no massive particles, and therefore no clocks and no concept of time measured by massive objects. In this timeless, massless limit, the geometry of the dying universe is conformally equivalent to the geometry of the Big Bang of the next eon, and the transition between the two is mediated by a conformal rescaling of the metric that maps the smooth, featureless heat death into the hot, dense initial state of the next Big Bang. The specific imprints of the previous eon in the CMB, in Penrose's picture, are the concentric rings of anomalously low temperature variance, the Hawking points that we have mentioned multiple times across these nights. The Hawking points are the imprints of the final evaporation events of supermassive black holes in the previous eon, events that released enormous bursts of Hawking radiation that crossed the conformal boundary and appeared as specific localized anomalies in the temperature of the CMB of the current eon. Penrose and his colleagues claim to have found evidence for these features in the CMB data, and the debate about whether the claimed features are statistically significant is ongoing. The next generation of CMB surveys will provide the data needed to definitively test this prediction. The ekperiodic and cyclic picture gives yet another specific view. The universe before the Big Bang was a contracting phase of a universe that had previously been expanding, and the contraction was driven not by the quantum gravitational bounce of loop quantum cosmology, but by the attractive force between two extra-dimensional branes that were moving toward each other through a higher-dimensional bulk space. As the branes approached each other, the energy density in the directions perpendicular to the branes increased, eventually producing the hot, dense state of the Big Bang when the branes collided. The specific density fluctuations produced by the ekpyrotic contraction, the scale-invariant scalar spectrum with negligible tensor component, are the observational signature that distinguishes the ekpyrotic scenario from inflation and from loop quantum cosmology. What all three of these pictures have in common, loop quantum cosmology, CCC, and ekpyrosis, is that the Big Bang is a transition between two phases of a physical universe, not a creation event from nothing. The universe on both sides of the Big Bang is described by the same fundamental physical laws, and the specific properties of the post-Big Bang universe are derived consequences of the dynamics of the pre-Big Bang phase and the transition. The arrow of time in our universe, the second law of thermodynamics and the direction from past to future, is derived from the specific low-entropy state produced by the transition, which in turn is derived from the dynamics of the pre-Big Bang phase. The Big Bang is the middle of the universe's history, not its beginning. The observational tests that will constrain these scenarios over the next decade are organized around four main observables. The first is the large-scale CMB power spectrum, specifically the amplitude of the temperature anisotropies at the lowest multipoles. The suppression at low multipoles predicted by loop quantum cosmology and the specific Hawking point features predicted by CCC are both in principle detectable by the next generation of CMB experiments, though the statistical challenges are significant because the lowest multipoles are inherently poorly sampled by the cosmic variance of a single sky. The second observable is the primordial gravitational wave background, specifically the tensor-to-scalar ratio R and the spectral tilt of the gravitational wave spectrum. Standard inflation predicts a specific value of R that depends on the energy scale of inflation, with a nearly scale-invariant gravitational wave spectrum. Loop quantum cosmology predicts a suppressed tensor spectrum. Ekpyrosis predicts essentially no primordial gravitational waves. CCC predicts a specific gravitational wave background from the previous eon that would appear in the CMB B-mode polarization at specific scales. The next generation of CMB polarization experiments, including the Simons Observatory, CMB S4, and the Lightbird satellite, will measure R to a precision that distinguishes between these scenarios at high statistical significance. If primordial gravitational waves are detected at a level consistent with high-energy inflation, it argues against the ekpyrotic scenario and against many variants of the bounce scenarios. If they are absent down to very low values of R, it argues against high-energy inflation and is consistent with the ekpyrotic and some bounce scenarios. The third observable is the non-Gaussianity of the CMB, encoded in the higher-order correlations of the temperature anisotropies. Standard inflation predicts small non-Gaussianity of a specific type and amplitude. The ekpyrotic scenario predicts a specific form of non-Gaussianity that is different from the inflationary prediction. Loop quantum cosmology bounce models predict non-Gaussianity from the quantum gravitational corrections at the bounce. CCC predicts non-Gaussianity from the specific pattern of Hawking points. The measurement of non-Gaussianity has been significantly constrained by Planck, with the current data consistent with standard inflation, but the next generation of experiments will push the constraints significantly further, potentially revealing non-Gaussian signatures that distinguish the pre-Big Bang scenarios. The fourth observable is the stochastic gravitational wave, background at frequencies accessible to space-based and ground-based gravitational wave detectors. The pre-Big Bang scenario of Gasparini and Veneziano predicts a blue gravitational wave spectrum that rises toward higher frequencies, which would be detectable by LISA in the millihertz band, and potentially by the Einstein telescope and cosmic explorer in the audio band. The ekpyrotic scenario predicts a gravitational wave background from the brain collision, whose amplitude and spectrum depend on the specific details of the collision dynamics. Loop quantum cosmology predicts a gravitational wave background from the pre-bounce contracting phase that is modified by the bounce dynamics. Each of these predictions has a specific frequency dependence and amplitude that can in principle be compared to observations from the network of current and planned gravitational wave detectors. The combination of CMB observations and gravitational wave observations, together with the high redshift galaxy observation from the James Webb Space Telescope and future telescopes, the 21-centimeter line observations from the Square Kilometre Array, and the baryon acoustic oscillation measurements from Daisy and Euclid, will provide the most complete and most constraining picture of the early universe ever assembled. This multi-probe approach is essential because no single observable can definitively distinguish between all the proposed pre-Big Bang scenarios, but the combination of multiple observables, each sensitive to different aspects of the early universe physics, can potentially discriminate between them. The timeline for this discrimination is roughly a decade to 15 years. The Simons Observatory is beginning operations now. CMB S4 is planned for the early 2030s. LightBird is planned for launch in the late 2020s. The Square Kilometre Array is under construction and will have significant science output in the early 2030s. The Einstein telescope and cosmic explorer are in the planning and design phase, with operations possible in the 2030s and 2040s. The James Webb Space Telescope is operational now and will continue producing data for many years. The combination of all of these datasets, analyzed within consistent theoretical frameworks, will provide the observational foundation for answering the question of whether the Big Bang was a beginning or a middle. Whether the answer will be decisive, whether it will clearly favor one scenario over all the others or will narrow the field significantly, depends on what the universe actually did in its earliest moments. If the Big Bang was a simple inflationary event with no pre-inflationary phase, the next generation of experiments will find CMB and gravitational wave signals consistent with standard inflation and no anomalies at large scales. If the Big Bang was preceded by a loop quantum cosmology bounce, the experiments will find a suppression of power at large scales and a tensor spectrum suppressed relative to the standard inflationary prediction. If the Big Bang was an ekpyrotic brain collision, the experiments will find essentially no primordial gravitational waves. If the Big Bang was a conformal transition from a previous eon in the CCC sense, the experiments will find specific Hawking point features in the CMB B-mode polarization. Each of these outcomes is distinguishable from the others at some level of observational precision, and the next generation of experiments will achieve the precision needed to make at least some of the distinctions. The probability that the next decade of observations will provide a definitive answer to the question of whether the Big Bang was a beginning or a middle is uncertain, but the probability that it will significantly narrow the range of viable scenarios is high. The frontier of our knowledge of the early universe is about to advance significantly, and the question of what came before the Big Bang is about to become more constrained than it has ever been. What would it mean, scientifically and philosophically, if the observations clearly favor a pre-Big Bang scenario, if the specific fingerprints of a prior phase are confirmed in the CMB and in the gravitational wave background? The scientific implications are straightforward. It would confirm that the Big Bang was a transition between two phases of a physical universe, not a creation event. It would provide the first observational evidence for physics beyond the Planck epoch, physics that is currently beyond the reach of any theory we have. It would constrain the specific form of that physics in ways that would guide the development of the theory of quantum gravity. And it would provide the first direct observational contact with a regime of physics, the quantum gravitational regime at densities above the Planck density, that has so far been accessible only through theoretical extrapolation. The philosophical implications are deeper and more difficult to assess. A confirmed pre-Big Bang scenario would be the most significant revision of our understanding of the universe's history since the discovery of the expanding universe in 1929. It would transform the Big Bang from an absolute beginning, a moment of creation, into a transition, a middle chapter of a longer story. It would make the question of what the universe was like before the Big Bang a scientific question with a specific physical answer, rather than a metaphysical question outside the reach of science. And it would raise, with new urgency and new specific content, the question of how far back the story goes. If the Big Bang was a transition from a contracting phase, what caused the contraction? If it was a brain collision, what caused the brains to approach each other? If it was a conformal transition from a previous eon, what caused the previous eon to reach heat death and transition? Each answer opens a new level of the question. This regress of what's and whys is not a defect of the pre-Big Bang scenarios. It is a feature of any scientific explanation that the explanation itself becomes the object of the next question. Newtonian gravity explains the orbits of the planets, but raises the question of what gravity is. General relativity explains gravity as the curvature of spacetime, but raises the question of what spacetime is at the quantum level. Quantum gravity will explain the Planck epoch, but will raise the question of what preceded the quantum gravitational state. Science has always been characterized by this regress, and it is not a sign of failure but of progress. Each answer reveals a deeper question, and the revelation of the deeper question is itself a form of knowledge. The possibility that the regress never ends, that there is no final answer, no bedrock below which there are no more questions, is one that some physicists and philosophers find troubling and others find liberating. If the universe has no beginning, if the question of what came before can always be pushed further back, then there is no ultimate explanation of why the universe exists or why it has the properties it has. There is only the endless chain of physical causes and effects, each one determined by the previous one, extending backward without limit. The universe simply is and has always been, and the question of why it exists has no answer because there is no state of non-existence from which it came. This picture, in which the universe is eternal and self-sustaining, without beginning or end in the ultimate sense, is in some ways more challenging to human intuition than the picture of a creation event. Creation from nothing is intellectually troubling but emotionally comprehensible. We understand beginnings, at least locally. We have personal experience of things coming into existence, of states changing from non-being to being. A universe without a beginning has no analog in ordinary experience. There is no moment before which it did not exist, no state from which it emerged, no transition from non-existence to existence. It simply always was, in whatever form the quantum gravitational laws permit. The human mind has difficulty with this. The concept of an eternal universe, one without a beginning, runs against the deep intuition that everything has a cause, that every state was preceded by another state, that the chain of causes must terminate somewhere. But this intuition, which is reliable and productive in the context of ordinary experience, may simply be wrong at the cosmic scale. The laws of physics, as we currently understand them, do not require a beginning. They describe the evolution of physical systems from given states to other states, and they are consistent with the universe having always existed in some form, evolving from state to state according to the laws, without any first state. The physicist and philosopher Max Tegmark has proposed an even more radical version of this picture, in which the universe is not just eternal, but is itself mathematical. In Tegmark's mathematical universe hypothesis, all mathematically consistent structures exist physically, not just our universe with its specific laws and constants, but every possible mathematical structure, every universe that can be described without logical contradiction. Our universe is the specific mathematical structure in which we find ourselves, and it exists for the same reason that all mathematical truths exist. Because mathematical existence is the only kind of existence there is, and mathematical structures do not need to be created or caused. They simply are, necessarily, as necessary as the truth that 2 plus 2 equals 4. The mathematical universe hypothesis is philosophically provocative and scientifically difficult to test, because a hypothesis that says all mathematical structures exist makes no specific prediction about which structure we should find ourselves in other than the anthropic selection of a structure hospitable to observers. But it represents an extreme version of the direction in which the pre-Big Bang cosmology is pointing, toward a universe that does not need to be created, because it does not need a cause, a universe whose existence is as necessary as the existence of mathematical truth, as fundamental and as inexplicable in terms of anything deeper as the fact that logic works. We are a long way from resolving these questions. The specific empirical questions, whether there are Hawking points in the CMB, whether the power spectrum is suppressed at large scales, whether there are primordial gravitational waves or not, are being addressed by ongoing and planned observational programs that will produce answers within the next decade. The specific theoretical questions, which quantum gravity framework correctly describes the Planck epoch, what the quantum state of the universe was in the pre-Big Bang phase, how the entropy reset occurs at the bounce or transition, are being addressed by ongoing theoretical work in loop quantum gravity, string theory, and quantum cosmology. And the philosophical questions, what it means for the universe to have no beginning, what kind of existence a universe without a first cause has, whether mathematical existence is the deepest kind of existence there is, are being addressed by a smaller number of thinkers working at the intersection of physics and philosophy. The answers will not all come at once. The observational answers will come first, as the data from the next generation of experiments constrain the theoretical possibilities. The theoretical answers will come as the quantum gravity frameworks mature and make more specific and more reliable predictions. The philosophical answers may come last, or may remain permanently contested, as philosophical questions often do. But the trajectory is clear. The question of whether the Big Bang was a beginning or a middle is being transformed from a philosophical question into a scientific one, and the scientific investigation of it is proceeding with the tools and the methods that have made science the most reliable way of understanding the physical world. Tonight, in the quiet of the hours when large questions become approachable, we have followed that investigation from the wall of the Planck epoch through the competing proposals for what preceded it, through the observational programs that will constrain those proposals, through the philosophical implications of a universe without a beginning, to the edge of what is currently known. The edge is not the edge of what can be known. It is the current position of a moving frontier, a frontier that has been advancing for a century and shows no signs of stopping. The universe is old enough and transparent enough and close enough to understand, with the right instruments and the right theories, that the question of its own beginning or middle is within reach of a scientific answer. What that answer will be is not known. The universe may turn out to have had an absolute beginning, a quantum gravitational state from which it emerged without prior cause, described by the no-boundary wave function or some variant of it. The universe may turn out to have no beginning, cycling through bounces or brane collisions or conformal transitions without limit, with the Big Bang as one of an infinite sequence of transitions. The universe may turn out to be one of many in an eternal inflating background, each bubble universe having its own local Big Bang, but the background having no beginning because it has been inflating forever, or having a beginning in some quantum gravitational state from which the inflation emerged. Each of these possibilities is consistent with what is currently observed and with the current theoretical frameworks. Each of them changes, in a specific way, the picture of where we are and what we are part of. An absolute beginning means we are in the one and only universe, the unique outcome of a specific quantum gravitational event that happened once and produced everything. No beginning means we are in one of an infinite sequence of phases of a universe that has always existed, our Big Bang being a transition in an eternal process. An inflating multiverse means we are in one bubble among infinitely many, our specific physical constants, and our specific Big Bang being one realization among all possible realizations. In all three of these possibilities, the specific here and the specific now are what they are. A point in the stelliferous era, in a specific galaxy in a specific supercluster, in an observable universe 46 billion light-years in radius. At a moment when the universe is old enough for complexity and life and minds to exist, and young enough for stars to still be burning. This specific location in space and time is real regardless of which cosmological picture turns out to be correct. The night is real. The stars are real. The photons arriving from every epoch of the universe's history are real. The question of whether the Big Bang was a beginning or a middle is real and important and currently unanswered. But the answering of it will not change the fact that the stars are burning right now, in this specific era of this specific universe, and that the light from them is crossing the space between them and here at this specific moment. The universe may have had a beginning, or it may have been a middle all along, a transition in an infinite process that preceded it and will continue after it. Either way, the specific moment of this transition that we call the Big Bang, 13.8 billion years ago, produced the conditions from which everything we can observe has evolved. The specific initial conditions of the post-Big Bang universe, whether derived from a quantum gravitational bounce or a brane collision or a conformal transition or an absolute quantum gravitational creation, produced the specific pattern of density fluctuations that grew into the cosmic web, that produced the galaxies, that produced the stars, that produced the heavy elements, that produced the planetary systems, that produced the conditions for life, that produced the minds that are now asking what came before it all. The chain of causation runs from whatever the Big Bang was to this specific night, unbroken and lawful all the way through, governed by the same physical laws at every step. That chain is what makes the question scientific. The scientific investigation of the chain, extended backward through the Planck epoch to whatever preceded it, is the project of quantum cosmology, and the project is real and ongoing and making progress. The answer to what the Big Bang was is not yet known. The direction in which the answer most likely lies, toward a middle rather than an absolute beginning, is the direction that the weight of theoretical argument currently points. And the specific program of observations that will constrain the answer is underway, collecting data from the oldest light in the universe, and from the gravitational waves that traverse the universe, and from the first galaxies that the James Webb can see. The wall at the beginning of time is real, but it is not permanent. It is the current limit of our knowledge, not the edge of what exists. Whatever is on the other side of the wall, whatever the universe was in the Planck epoch and whatever preceded the Planck epoch, is part of the same physical reality as the stars above and the ground below and the specific moment of tonight. It is not inaccessible in principle. It is accessible to the physics that we are in the process of developing, the physics of quantum gravity that will one day describe the Planck epoch as accurately as classical general relativity describes the orbit of Mercury, or as quantum chromodynamics describes the structure of the proton. The development of that physics is the work of the current generation and the next, and the question it will answer is the oldest and deepest question that the physical universe can ask about itself. There are nights that are good for sitting with the large questions, the questions that are too large for the day, but that the night, with its specific quality of stillness and space, makes possible to approach. The question of whether the universe had a beginning is one of those questions. It is large enough that no single night can contain it, and specific enough that the nights spent with it are not wasted but productive, each one revealing another aspect of the problem and another thread of the theoretical landscape, and another hint from the observational data about which way the answer points. Tonight has been one of those nights. The universe may have been a middle all along. The Big Bang may have been a transition, not a creation. The specific hot, dense state from which our universe expanded may have been produced by a process that preceded it, a process that was itself physical, governed by the laws of quantum gravity, continuous with the universe we inhabit rather than separate from it. The question is not yet answered. The investigation is ongoing. The observational programs are running. The theoretical frameworks are being developed. The answer is coming, slowly and carefully, and with the patience that science requires when it is working at the edge of what can be known. And in the meantime, the stars are burning. The universe is expanding. The photons from the surface of last scattering, the oldest light we can detect, are arriving from every direction simultaneously, carrying information about the state of the universe 380,000 years after the Big Bang, or after the bounce, or after the brain collision, or after the conformal transition. The specific pattern of those photons, the tiny temperature variations across the microwave sky, contains, perhaps, the fingerprints of what came before. We are reading them. We have been reading them for 60 years, since Penzias and Wilson first detected the hiss of the cosmic microwave background in their microwave antenna in New Jersey. We are getting better at reading them. And what they are telling us, slowly and quietly and with the specific authority of the oldest signal in the observable universe, is that the story began earlier than we thought, and that the beginning, if there was one, was further back than the first flash of the Big Bang. Thank you for spending this night here at the edge of what we know about where we came from. This is Dusk and Discovery. The universe may have been a middle all along. Sleep well.